All right. Good morning, everyone. Welcome to my office hours. Before I start, I'm going to answer questions, any questions that you guys may have. If you don't, then I'm just going to get straight into it. I don't see any questions right now, so I'm just going to go ahead and into it. If there are, then I'll just pause and read out the question for you guys and everything. So, yeah. So, what we've been going over for the past 2 days is NMR spectroscopy. So, what we've been through before is IR spectroscopy and mass spectroscopy. Mass spectroscopy went over the mass of the whole molecule. IR spectroscopy goes over the functional groups. NMR spectroscopy gives us more information about the actual structure because it tells us how many different types of carbons, how many different types of hydrogens there are, and how they react with each other. But that'll become more clear once we get into it a little bit more. So when we're doing nuclear magnetic resonance spectroscopy, which is NMR spectroscopy, when we have stuff with odd numbers, like nucleuses with odd numbers, then they can be studied with NMR spectroscopy. And so the main two that we're going to be focusing on is proton spectroscopy and carbon-13 spectroscopy. But honestly, the one that I see mostly is proton spectroscopy, which is H1 spectroscopy. Um, so when we're looking at NMR, what happens is when we apply a magnetic field, the energy level changes and it goes from an alpha spin state to a beta spin state, or vice versa. And so then we can use that to measure the amount of energy it absorbs and plot that on a graph. Let me see if I can see if there's a graph right here. Yeah, so we can measure them on this graph. So we measure how much it absorbs and plot this on this graph. I wouldn't know too much about the actual math. I would focus more on how to read the graph and how to understand the graph. So let me go back real quick, just to make sure I didn't miss anything. Let me make sure there are no questions. Okay, so again, like I said before, when we apply magnetic field, which is essentially applying energy, the spin state is going to swap from a low energy spin state to a high energy spin state. And so we can measure that using NMR. And then we can plot that on the graph using something called ppm, parts per million, but don't worry about that. Just worry about how it looks on the graph. Like we're looking at 109876. We're not too much worried about ppm because that's sort of like just the uh, sort of arbitrary word that we use for it. Like we use meters or seconds. Right here, we're going to use ppm. So this is an H1 NMR spectrum, so like a proton NMR spectrum. And so what this is measuring here, it's measuring the protons, not the whole molecule. This graph here I don't like because it shows you parts of the whole molecule, but what it's actually measuring here are the two different types of protons. So we have this CH3O on the left, and then that's going to be corresponding to one type of proton, and the CH33C is corresponding to a different type of proton. This graph is not about the actual molecules, it's about the hydrogens. Okay. So when we're looking at the signals, the number of signals that we have are going to be corresponding to the amount of types of hydrogens that we have. So how to tell if a hydrogen is different from another one is basically we're going to be looking at the different sorts of environments they're in. So if you look at this first one, both of these hydrogens are the exact same because they're both attached to, so like on the right, this CH3, the H's are all attached to one carbon, which are attached to one oxygen, which are attached to another carbon. And the same thing on the left, where the three hydrogens are attached to a carbon, attached to an oxygen, attached to another carbon. So they both have the exact same bonds and the same environment. That's what makes them the same. If we look at this middle example with the Cl, we can see here that on the left, the blue, we have CH3. Those H's are attached to a C, which are attached to a CH2, which are attached to a Cl. If we look at HB, which is the red, those H's are attached to a C, which is attached to a CH3 and a Cl at the same time. So they have different bonds, and thus they have different types of environments. Essentially, what you're going to do, or at least what I do, is I count the number of hydrogen or the number of carbons that look um, different, and then what you do is you see how many of those carbons have hydrogens, and then you are able to tell how many different types of hydrogens there are. Let me see if there's an example here. There's not, which is really cool, but so if we look here at this very middle example with Cl on one side and Br on another side, if we look at this, we see we have 1, 2, 3 carbon types, which means that we have 3 different hydrogen types because we know all of those carbons have hydrogens attached to them. If one of these carbons did not have hydrogens attached to them, then there would be no peak associated with that because there are no hydrogens to make that peak. That's something important to look out for because that's something that I see a lot of people messing up on is when they see a carbon that doesn't have any hydrogen bonds because we're looking at the line angle structure. And remember, we don't normally draw the actual hydrogens on the line angle structure. And so if we see a carbon with 4 bonds and you just forget to count those bonds, you might be inclined to count that as a different type of hydrogens. You just have to look out because not all carbons are going to have hydrogens attached to them. Okay? Are there any questions about how to tell if the environment is different between 2 hydrogens? I'm going to take a sip of water. Okay, so since there aren't any questions, I'm just going to continue on. So another type of hydrogen that is there that won't be as obvious to count. Oh, is there a question? Or did I hear things? I think. Oh, somebody's. I'm just gonna mute. I'm gonna mute Trammy, and she can put in her questions on the question board. So anyways, sorry. Back to this stuff. Something that's not as obvious to see is if we're looking at a double bond and we're trying to determine if those hydrogens are different or if they're the same and they'll have the same type of signal. In order to be able to tell that, what you have to do is you have to see if they're cis or trans or cis or cis to different things. So if you look at this first one, 1,1-dichloroethylene, the H is cis to, the first H, the top H is cis to Cl and the bottom H is cis to Cl, so they're both in the same type of environment. However, when we look at the next example, 1-bromo-1-chloroethylene, HA, the top one, is cis to Cl, and HB is cis to Br. So they are in different environments, so they're different types of hydrogens, and they'll have different signals on an NMR spectrum. Finally, looking at chloroethylene, this one's going to have 3 different signals, because if we look at HB, HB is cis to Cl, HC is cis to another H. And then HA is on a completely different carbon, so we know that one's going to have a different type of environment. And so then that's going to have a different type of signal. Okay? And then we're looking at cyclochloro propane or any cyclopropane. And we look here, we have to count hydrogens as okay, so if we look at this one on the right, all of those hydrogens are equivalent because all of the carbons that they're attached to are in similar environments, so all of the H's are in the same environment. When we look at chlorocyclopropane, this top carbon, or I guess the carbon that's connected to the Cl, is going to be completely different from the other 2 carbons. However, the other 2 carbons have the same types of bonds. They're bonded to each other, and then they're bonded to that carbon with a Cl. So both of those carbons are in the same environment, but the hydrogens are not. Because one of them, one of them is going to be cis to Cl, and one of them is going to be cis to the other hydrogen. So they're all going to have different signals. The difference between this and something that we would usually see is that we see two hydrogens on different carbons having the same signal. This is because those carbons, if that Cl weren't here, would be completely equivalent. Like if we look at the left at just the cyclopropane, they're all perfectly equivalent. But here, while they are equivalent, the hydrogens on them are not. So the hydrogens are going to be associated with other hydrogens on the equivalent carbon. I know that might be confusing. So there is a question here. So for the chloroethylene, it's 3, even though the HA is cis to HC. Yes, because if we look at these two different carbons, so like I said, if we look at the two carbons and if they're in different environments, then they're going to have different types of hydrogens. So we know the carbon on the left, which is attached to a Cl, and the carbon on the right, which are attached to just H's, are different. So the hydrogens attached to them are going to be different. However, the carbon with the two hydrogens attached to them have two different hydrogens because one is cis to Cl and one is cis to HA. Even though HA and HC are cis to each other, they are not equivalent because they are on different carbons with different bonds. Okay, did that answer your question? Yes, okay, good. All right, so I'm going to go ahead and move on. This sort of stuff you're more likely going to see on ACS rather than any of Dr. Dowdy's test, but I would keep it in mind. Okay, so homotopic, enantiotopic, and diastereotopic protons. So when we're looking at to see if hydrogens are equivalent, one trick we can do is to see if they're homotopic, enantiotopic, or diastereotopic. I'm awful at saying these words. Please don't make fun of me. So for this first one, HA and HB are homotopic. So the way that we are able to tell that is we replace each one. So we replace HA with a placeholder Z and HB with a placeholder Z. So if we look over here, so if we look at this first homotopic and we look at the first product, we replaced HA with Z. And then if we look at the second product, we replaced HB with Z. And we can see here that there is no chiral center. So they can't be enantiomers to each other, so they have to be the identical products, so they have to be homotopic, and so those H's are equivalent. Okay? And an easy way to be able to tell if things are homotopic is to see if the carbon attached to the two hydrogens would become a chiral center if you replace one of them with a different group. Here we can see that the carbon has two methyl groups attached to it, two of the same group, so it's impossible for it to be a chiral center, so they have to be identical products. If we look at this carbon here, we can tell that if we replace HA or HB with another group, there will be a chiral center. What's important to note is that this is the only chiral center in the molecule. So we're going to get enantiomers. If there is only one chiral center, then you're going to get enantiomers. If there are two chiral centers, one of which isn't changed by the substitution, quote unquote, it's going to be a diastereomer. Okay? So, just to reiterate, homotopic and enantiotopic, they're going to be equivalent. So both of those hydrogens are going to be the same signal. Okay? And if we look at diastereotopic, we can see here that the HA and HB, if replaced by a different group, they are attached to a carbon that would become a chiral center. However, there is a second chiral center in this molecule. If you look here, the carbon with the chlorine attached to it. And so if there are two chiral centers on here, and you replace one of the H's with another group and the other H with another group, you're going to get diastereomers. Just to do a quick review, enantiomers are enantiomers because their chiral centers are complete opposite. So if we look up at these two enantiomers above the diastereomers, the one on the left could be R and the one on the right could be S. They're completely opposite. For the diastereomers, the chiral center on the left with the carbon attached to the chlorine, it does not change between the two molecules. And so you have partial inversion, partial opposites, which makes them to be diastereomers. Enantiomers are complete opposites. Diastereomers are partial opposites when looking at them in relation to their chiral centers. Okay? Okay, so one more little review. If the HA and HB are homotopic, which means they make identical products when replaced with a filler group, or if HB and HA are enantiotopic, which means they form enantiomers when they're replaced by a placeholder, they're going to be equivalent hydrogens. If they're diastereotopic, which means if we replace HA or HB with a placeholder, and they create diastereomers, they are not equivalent and they will have different types of peaks on the NMR spectrum. Okay? So here are some examples. This first one, we're just going to go through these really, really quickly because I know we went through them in class. This first one, if you look at that center, or if you look at the carbon attached to the two hydrogens, that cannot be a chiral center because it has two of the same group on either side. So these two are going to be homotopic, and so they're going to be equivalent hydrogens. If you look at the next one, we can see there, yes, that will the carbon with the hydrogens will make a stereogenic center or a chiral center, but there are no other chiral centers on this molecule, so it's going to be enantiotopic. And if we look at this final one, the carbon attached to the two hydrogens, it will make a chiral center, and we have another chiral center on the left carbon. I know you can't see my mouse, but I'm going to zoom in real quick and zoom in on the hydrogen that, or the carbon that's another chiral center. Okay, I can't zoom in that far. But if we're counting the parent chain, which is just the horizontal line angle structure, on the third carbon, that's going to be another chiral center. So here we have a potential chiral center where the two hydrogens are and a current chiral center. So that means that these two hydrogens are diastereotopic, and so then they're going to have the different signals on the NMR spectrum. Okay? Okay, so now we're going to be talking about shielding and deshielding. This is what we got into today in class, at least for the 11:30 class. The 2:30 class may be a little bit different, but you should get to this eventually if you haven't yet. So the shielding and deshielding effects. So when you have something shielded, that means it's going to have a lot of stuff around it. It's going to be shielded from the NMR. It's shielded from the magnetic energy and stuff that it's being bombarded by. So when it's shielding, it's going to shift upfield because it's going to be less affected by the NMR. So it's going to have lower numbers. And remember, the NMR graph goes from greatest to least from left to right. So when we are shielded, we're being shifted upfield to lower numbers. Okay? And if we are deshielded, which means we do not have electrons around it, we are not being shielded by those electrons, it's going to be more affected by the NMR resonance, and it's going to be shifted downfield to larger numbers. Okay? And now we're going to look at different factors that will cause the proton to be shielded or deshielded. So if we're looking at this chart, what we're going to do is we're sort of going to compare some of the more obvious ones. So like if we look here at just the first one on the top left with the carbon attached to different alkyl groups, so like a primary carbon, a secondary carbon, a tertiary carbon. If you look here, the primary carbon is the most deshielded, the most shielded because it has the lowest number. And then the secondary is the next most shielded, and the tertiary is the next most shielded. So the more alkyl halides that you have, the less shielded that hydrogen is going to be. Okay? Does that make sense? Of course, you don't have to memorize these numbers. You'll sort of get a better feel for them if you understand the logic behind them. So let's compare the tertiary, secondary, primary carbons, with something like an carboxylic acid, which is it's the fourth one down on the right row. So if we look at the carboxylic acid, that hydrogen is shifted way downfield, which means it's a very deshielded, which makes sense because we have oxygens both pulling at that hydrogen, pulling electrons away from it, deshielding it, taking away its electrons, okay? Okay, so inductive and substitution effects. So here, the more inductive it is, means the more electrons it's going to pull towards itself, the more electrons it's going to pull away from those hydrogens, and the more deshielded it's going to be. Okay? Same with these R groups, which are just alkyl groups. Okay? Okay, so something that's important to talk about is if we're talking about aromatic rings, which means, I'm going to scroll up, which means it's a benzene ring. So it's the second one down on the right row, which means every other bond is a double bond. That's an aromatic ring. And aromatic rings are pretty deshielded because the electron densities are above and below the ring and not at the hydrogens. Again, this is something that's more relevant in Orgo 2, so I wouldn't worry about it too much. If you really want to, I would look at the table that is right here and compare it with these pictures that we have right here. So we can see here that the electrons are generally above and below the ring and not near the hydrogen. And if we look at the alkene, which is the one on the left, which has sp2 hybridized carbons, the electron density is above and below the double bond. So the hydrogens are going to be generally shifted downfield because they're deshielded because all of the electrons are near the double bond. Okay, and finally this triple bond, it's going to be shifted downfield again for the same reasons that the double bond was, because most of the electrons are going to be around that triple bond and not around the hydrogen. So if you look at the chart here, so the triple bond, it shifted downfield, but like only slightly because it is sort of near the hydrogen. And then comes the double bond, and then comes the benzene ring, and then all of this stuff with the induction effects. Okay? Again, this stuff is stuff that's more relevant in Orgo 2. Just sort of know about it in the back of your mind. Characteristic values of chemical shifts. This is less important than knowing the characteristic values of IR spectrum because, yes, while these will generally tell you the structure of a molecule, using the IR spectrum for the functional groups is way better, way easier, and it makes much more sense. But this is sort of the pattern of shifting where we have single bond, double and triple bond, single bond with an alkyl halide, or single bond alkyl halide, double bond aromatic ring, oxygens pulling the electrons away. Again, if you want to memorize these, you can, but it makes more sense if you understand the logic behind it, I have found. Okay, so integration, if you're not big into math, what integration means is the area underneath the curve. So if we're looking at these different curves here, so CH3O versus CH33C, if we're looking at these curves, so this curve on the right is 3 times the amount of the curve on the left. So that means its relative area is 3 versus the relative area of this 1. So if you look, and if we look at the types or the number of each type of hydrogens, you can see the one on the left here, CH3O, that has three types of hydrogens, or three hydrogens of that type, sorry. And if we look at this one on the right, it has 9 hydrogens of that type. 3 times 3 is 9, which is the same ratio that we have of 1 to 3. This might make more sense if we do the next example. Okay, so here's disintegration. This one looks a little bit weirder than the last one because this one has something called proton splitting, but we will get into that in a little bit, not right now. Okay, so if we look at the area underneath these curves, we have 27, 40.2, 28.4, 42.2. Those numbers don't really mean much to us, but what we want to do is we want to find the relative area beneath each of them, which means we have to make the smallest one 1. So that means that we divide every single one of these numbers by the smallest number, which is 27 here. So 40.2 divided by 27 is about 1.5. 28 divided by 27 is about 1, of course. And then 42.2 divided by 27 is about 1.5. So we have 1, 1.5, 1, 1.5. 1.5 isn't a whole number, and we want whole numbers to know the ratios in a little bit clearer way. So what we're going to do is we multiply all of these numbers by 2. Yeah, he doesn't have the math here. So what we do is we multiply all these numbers by 2 to make them into whole numbers. So before we had 1, 1.5, 1, 1.5. When we multiply it by 2, we have 2, 3, 2, 3. So the relative ratio of hydrogens is 2 to 3 to 2 to 3. Now, again, these numbers aren't exactly the number of number of hydrogens associated with each one of these peaks. You could have a different amount of each. Like if you multiply all this by 2, you would have 4 to 6 to 4 to 6. That could be your number of hydrogens. All that this is telling us is the ratio of different hydrogens to each other. Okay? So the next thing we're going to get into is something called spin splitting. This is pretty important because it tells us exactly how many hydrogens are next to different types of hydrogens. So let's look at the blue CH first. So the blue one here, if we look at the actual molecular structure, we have CBrCH2, CBr2H. And so if we look at CH, it has 3 peaks, so it's called a triplet. A very novel name, I know, but it has 3 peaks, so it's a triplet. CH2 has 2 peaks, so it's a doublet. So where did these peaks come from? Well, these peaks came from the different hydrogens next to it. So if you look at CH and we look at the bond directly next to it, so 1 sigma bond, it's next to a CH2. Those 2 hydrogens split the signal of the 1 hydrogen into 3 signals. If we look at CH2, that signal of those types of hydrogens are split into 2 signals by 1 hydrogen. So to summarize, the spin splitting signal is going to be the number of neighboring hydrogens plus 1. So the CH has 2 neighboring hydrogens. 2 plus 1 is 3, so it has a triplet. CH2 has 1 neighboring hydrogen. 1 plus 1 is 2, so it has a doublet. Okay? And so what's happening here is, remember how we talked about how there are different types of energy states? This is sort of similar to that, in that when you have hydrogens next to it, you're going to have different types of spins. So like you can spin up or spin down, where the magnetic field is pointed up or the magnetic field is pointed down. This has to do with Chem 2 stuff. If you don't remember that, that's fine. We're not as worried about the science behind spin splitting versus being able to recognize and build a molecule from the spin splitting signals. So if you don't understand the science behind it, that's fine for the test, but I highly recommend learning about it so you're more prepared for Orgo 2 and stuff like that. And so there's like a specific way that these signals are going to split. So you see a triplet is split into 1, 2, 1. And this is because of the different ways that the hydrogen can absorb at. So it can absorb both A and B up, A down, B up, both A and B down. Again, this is stuff that you don't need to worry about for the test. So I would learn it later if you have the time. Okay? Um, Okay, and so then we're talking about multiplicity. So we can have a singlet, which is something that we're used to seeing, a doublet, which is what happens when you're split by 1H, a triplet, you're split by 2H's, a quartet, 3H's, quintet, 4H's, and so on. You're not really going to be asked to be able to discern between sextet, septets, all that stuff. Usually they're going to tell you if you have like a quintet, a triplet, a septet, all that stuff. Yes, there's a question in the chat. So it doesn't matter how many hydrogens are on the carbon, just the adjacent hydrogens plus one. Exactly. Let me scroll back up. So for example, if instead of being a CH, the CH was a CH2, it would still be split into a triplet. Okay? And same with this one, if the CH2 was a CH and there was one adjacent hydrogen, it would still be split into a doublet. Okay, it does not matter how many equivalent hydrogens are on that peak. It's about the adjacent hydrogens. Did that answer your question? Okay, good. Okay, so splitting of the signals. So they have to be pretty close together. They have to be either on the same carbon or on like carbons that are right next to each other, but separated by one or less sigma bonds. The one on the right here, that's separated by two sigma bonds, so they're too far apart to split each other. Okay? When we're talking about geminal hydrogens, that means they're on the same carbon. I like to think about it as, Gemini, that's a twin. Geminal means they're on the same carbon, so they're twin hydrogens. I don't know. That helped me remember it. And vicinal means they're in the same vicinity, but they're not on the same carbon. Um, we would see more splitting of geminal hydrogens if we're looking at stuff like double bonds or stuff with cis or trans like we talked about before. Okay, so HMR of OH protons. So in this example, we're demonstrating that the HC hydrogen is too far from the CH2 and CH3 hydrogens to be able to be split by it. So this hydrogen is attached to an oxygen, which is attached to the carbon. So this carbon is too far away, or the hydrogens on HB, the HB hydrogens, are too far away to split the HC hydrogen. However, HA and HB are right next to each other. HB is a neighbor to 3 hydrogens, so it's going to split into a quartet because 3 plus 1 is 4. HA is next to 2 hydrogens, so it's going to split into a triplet because 2 plus 1 is 3. Okay? Okay. So the next thing we're going to be getting into, so the stuff with H1 NMR or proton NMR is what we're going to mostly be seeing. What we're talking about next is 13 carbon NMR spectroscopy. We don't see this often, but it's the same concept as H1 NMR spectroscopy. All of the carbons have to have different environments to be read as different signals, and they're going to be shifted up or down depending on the shielding or deshielding effects. So if we look at this example, we have 2 different carbons, so we have 2 different signals. The C double bond to an O has less electron density because all of the electrons are being pulled towards that oxygen, so it's shifted downfield. Okay? Okay, so we're going to continue on. So, like I said before, we have to look at the different carbons that are in different environments. So if you look at dimethyl ether, those have the same exact environment, so they're going to have the same signal. Chloroethane, we have 1, 2 carbons with different connections, so they're in different environments, so they're going to be 2 different signals. And then methyl acetate, We have 1, 2, 3 different carbons, all that stuff. If we look at these examples here, it might be a little bit difficult for you to tell which ones are going to have different signals. But let's look at this first one here. We can tell that there's a line of symmetry down the middle. So the carbons on the left are going to be exactly the same as the carbons on the right because of that line of symmetry. So because they have the same types of environments. So we're only going to have 1, 2, 3 different types of signals. The two hydrogens on the the two carbons on the very left match the two carbons on the very right, and then the middle carbon has its own signal. Okay? Okay, so then the second example is going to have 1, 2, 3, 4 different types of carbons because the carbons on the very end, making that tert butyl, yeah, sorry, making that tert butyl, those all carbons have the same type of environment because they have the same types of connections. So we only have 4 different types of carbons instead of the 6 or the 7 that we can see here. Okay? And then this double bond one. Yes, it's symmetrical, and yes, it's only going to have 2 signals because it is symmetrical, but it follows the same sorts of rules as the the different hydrogen signals. So if on the right here we had a different substituent than hydrogen on the other side of that double bond, then we would have different types of signals. However, since this is symmetrical and there are no different types of bonds, then it's going to be only 2 signals. Okay? So chemical shift in C13 NMR spectroscopy. Again, this is the same as hydrogen shifting. It's the more deshielded it is, the more downfield it's going to be. So it makes sense because the carbonyl is all the way down at the far left because that one's going to pull a lot of electrons from that carbon, or the oxygen is going to pull a lot of electrons from that carbon, sorry. And it just follows the pattern that we saw before in the hydrogen spectroscopy, okay? Okay, and so here's an example. I think we talked about this before. Again, CH3 is way upfield because it is not deshielded, it is shielded. And C double bond O is very far downfield because it is very shielded or very deshielded by the oxygen pulling those electrons towards itself. Okay? And so here are some more examples. So we have different types of carbons, A, B, C. I don't know why it's denoted like this, but we have A, B, C, and D. And all of these are going to have different shifts. Oh, I know. So if we're going from left to right, the one on the far left, the one shifted furthest downfield, that's going to be carbon D because that oxygen is pulling electrons towards itself, so it's going to be the farthest downfield. Okay? The one farthest upfield is going to be A because it's the farthest away from that oxygen, and it's going to be affected less by the deshielding effects and all that stuff. And then we just go A, B, C, or D. A is on the far right, and then B is the next one, and then C, and then D. That's why it's named that way. Okay? Okay, and so then that's the end of this PowerPoint. So I'm going to finish up a little bit early today to answer any questions that anybody may have. I'm going to go ahead and stop the recording, but if there are any pressing questions that I think are good examples or good questions, then I'll probably post them either in notes, in the GroupMe, just around everywhere. Okay? So again, oh, okay, so somebody has a question, so I'll keep recording while answering that question. Okay, so I've been asked to go back to slide 24. Okay, so is there a question about slide 24? Oh, okay, no, just somebody missed it. That's fine. So Trammy is asking how I got the different peaks for this graph. So if you look at HA, HB, and HC, I'm going to go back to the previous slide for a second. So we can see here that to be split, we have to be at least one bond apart and no more. Okay? And if we look here, that H is one bond to the O, and then that oxygen is bonded to another C. So to get to the next closest hydrogen, we have to jump 2 bonds. That is too far to be split, so HC is only going to have one peak. However, HB and HA are close enough to be split by each other. So HB is going to be split by 3 hydrogens, making it a quartet. HA is going to be split by 2 hydrogens, making it a triplet. Okay? Does that answer your question? Okay. And then another question was, can you help for how can you help us know how to find the exact structure based on only looking at the graphs? Um, this is more of a practice question. I would need like a specific example to be able to do that. Like if you have homework examples, you can send them to me and I will walk you guys through them. But I can't really do it off the top of my head. I'm really sorry. But essentially, what you need to do is you need to use the IR spectrum to find the notable functional groups, and then you're going to use the mass spectrum to figure out how many carbons that you have that are connected to those functional groups, and so on. And then you would use these NMR spectrums to figure out how those different atoms are arranged together. So, for example, this CH3CH2OH, it's going to have a very significant peak in the 3500, a really broad peak in the 3500 region because of that OH group. And then if we use the mass spec, it would tell us the total weight of it. So we can see we have 3 different types of protons. We can see the total weight, and we know that there's an OH group in it. Okay, and then if we know there's an OH group in it, we know that it's probably too far to be affected by the other hydrogens. So it's probably going to be our hydrogen that is not split. And then we would just go on from there. So it's just like writing down everything that you have. So you know you have an oxygen or an OH group. You know you have this certain mass. You know you have these different types of hydrogens. And you know that these hydrogens are splitting in different ways. And so then you put all of that together to figure out the actual structure. Okay? Okay, so I think that was all the questions, so I'm going to finish up for today. Go ahead and message me in the group me or in the Discord if you have any additional questions. Bye!